Okay, so we look at the, let me check. We actually look at the 3-bar crank slider, all right, 3-bar crank slider linkage. So we have this 6 equation here. Okay, so when we have questions, normally what are we going to do? So first of all, sure, we have to find all the value here and all the value here, right? Then only there is a possibility that we can solve the matrix at the middle here. Okay. So maybe you have these few minutes I will be a bit slow because I'm operating on the two system. I'm in the office. So the slide is on my laptop and I have another call on my office desktop. So I have to make sure you guys can hear me. Okay. So we have these 6 equations, okay, on this 3-bar crank slider linkage. So we have to find the things here. We have to calculate these two. Then only we can find the 6 unknown at the center there. Okay. So this is an example. We looked at it before, but we haven't solved it. So we have all these parameter here: crank uh, long, or sometimes we call it link length. Link length is 127 for link 2. Then we have the mass is central of gravity. Okay, so there's an angle given. Right, so means that the center of gravity is not sit at the uh, line center. We call it line center. And then also the mass moment of inertia is given. Right, so all the parameter is given here. Then link 3, we have the length 381, mass. Then the center of gravity also sit away from the line center, so which is 45 degree. And then the mass moment of inertia is 0.113 kilogram meter square. So also other value that we get. Right? So as I mentioned, theta 3, theta 4 is from position analysis. Then omega 2, omega 3, omega 4 is from the velocity analysis. And then we have alpha 3, all the acceleration, okay, is from acceleration analysis. Right? So it gives us the slider velocity. Then there is an additional of force on the link 3, right, on the link 3 at the position 68.6 and the 201 degree from the center of gravity. Right? So you have to basically take all this value here and then you have to refer back to the diagram we have. Okay, this one. Okay, so you have to refer all this back to the diagram. Okay, so now how we do it. So I also uploaded this one yesterday actually on the Weber, so you can download it. Okay, so this is what we are going to do. So we have to find one by one. So R12 is given a 76.2 mm. Okay. So at the angle of 270, so if you calculate it, 270 basically means your Rx is 0. So your R12Y is negative 0.0762. Okay. Then R32 is 0.719. Okay. So then with the angle of 28. So if you calculate that, maybe before we go there, so how you calculate the R12X? Okay. So you just take the R12, then this should be cos 270. Yeah. This is R12 sine 270. Okay. So the same thing go to the R32. So you get R32 cos 28. So you'll get this R32 sine 28. You'll get this. So as I mentioned that this question is very time consuming. It's not difficult. As long as you remember the X is cos, the Y is sine, then you have to calculate all this. But first you have to get all this. R12 is given. R12 is given as uh, the location of the center of gravity, right? From the line center, and then this angle you have to find carefully. Yeah. All right. Maybe let me. Okay, because if you look at that, the link 2, so link 2 now is 60 degree. Yeah. So for example, this is my 0, 02, so this is my link 2. So I have 60 degree here. Where you read the question, so it say that the theta 2 is 60. There is a theta 2. And then my center of gravity for link 2 is 76.2 millimeter at the angle of 30 degree from the line center. That's why you have to draw another line, because this is line center. Right? So you have to draw another one which is 30 degree, and then the length is 76.2. So your R12 is this one. Okay, that's why if you measure, maybe I use blue. So you have the local non-rotating coordinate system, the XY, X, Y here. That's why the angle that you measure now is 270. Right? That's why this is your R12. Okay. So if you want to find the R12X, it will be 0 because it sits at 270. R12Y, then it straight away is 76.2 millimeters. Okay, so you have to do one by one. Maybe we look at another one when we say R32. Am I right? So what is our previous one? Right, R32. Okay. Okay. So R32 is where? So if this is my O2 again, this is my link 3, okay? So just now we already found that 76.2 at the angle of 30. This is my R12. So R32 will be at, okay? So this is my R32. So I have my XY here, okay? So that's why, and I have to find where is the angle. What is this angle? Okay. So because we have this link length given 127, so I can find the length here. Right, so you use the cosine, so I can find R32 is 7 or 0.0762 square plus 0.127 square minus 2 AC, 0.0762, and then cos 30. Okay, so this is how we do it: 0.0762 square plus 0.127 square minus 2, 0.127, 0.0762 cos 30. So that is where we get 0.0719. Right? So that's why this one R32, after you square root the value, you get 0.0719. So there is the length of this. Then you also have to find this angle. Okay? Find the theta, maybe I say theta 332. Alright, so in order to find theta 32, you can use the sine rules. So we can find this angle first. Right? So what is this angle? So we label it as a beta, for example. So I can find, you still remember the sine rule? So if you have this A, B, and then C sine alpha, for example. So then I can have my 0.0179, sorry, 0.0719. Then you take sine 30 because that is the angle opposite the length 0.0719. Then equal to this one 0.127. This is mm, this is meter. So divided by sine beta. So from here I can find my sine beta. So it is 0.071, 0.127, 0.0719 times that. So we get it 0.8832. So then I can find my beta. Okay, I get my beta is 62. You find out that you get 62.03. But if you look at that, that is impossible to have 62 0.03, yeah. So it means that whatever we calculated is actually this angle, okay? So that's why the actual one, it should be uh, 180 minus 62.03. So we are getting 117.97. Okay. So means the actual one is 117 or 118, right, degree, right? That's why your theta 32 is the beta minus the angle. What is the angle of this between the total horizontal, the x-axis of the local non-rotating coordinate system to the R12. Since this one is 90, so that's why over here we are getting 90 as well. That's why we take the beta minus 90. Minus 90. So 118 minus 90, so we get 28, which is what we have in the book there, right? 28. So this is how we get all the numbers. So even though I show you, this seems to be very straightforward, but in order to find this, find this, you have to make a lot of sketch and calculation. So once we get these two values, then we can straight away find R32X, R32Y. So again, R23 is given in the question. So that is the center of gravity 228.6 mn at the angle of 45. So again, you have to recalculate the 45. Right? So in this case, if we refer back to the today my desk arrangement is not normal to what I used to, so I'm a bit slow. Okay, so you will be back to look at the diagram we have. Okay. So you have to take the theta 3. Oh. So you have to take the theta 3 plus the angle. Okay. Then only we can measure the R, so-called the R23 from the horizontal line. So we have to take the whole angle here. Okay, the theta 3 is given 99.59. So then the angle that we have is 45. Okay. Okay. Maybe I show you why we get that value. So now, oh, So what now happen is this is a coordinate system. Okay, so my link 3 is here. Okay, 99.59. Okay, so now my central of gravity is another 45 angle. Okay, so it's over here. So it says that this is 45 degree. But remember, the problem we are trying to solve is my R23, right, has to be measured from here. Okay, so that's why then you have to calculate what is at the actual this angle. Okay, so that's why we can find this. We can find this angle. For example, I say this is again beta. So my beta is 180 minus 45 minus 99.59. So we can take it 180 minus 45 minus 99.59. So we get 35.41 degree. So when we get this beta, basically this is the beta over here. So I can now find my angle here. This is the theta 23 here. Then we can take 360 minus the 35.41. So we will be getting 324.59, right? So this is how we get the angle for this R23, right? So that's why the R23 is given 324.5, right? So it's given here. So you have the length, you have the angle, then you can calculate x and y. Okay, so same as R13. Okay, so then you have to use the cosine rules to find this, and then use the sine rules. So this use sine rules, this use cosine rules. So to find the angle, then you'll find R13x, R13y. So RP given 68.6, and then it gives us 201 degree. Okay, so this one just take it from the books because this angle is measured directly from the center of gravity. Yeah. So then we can find RPX, where is my X, and RPY. Okay. Then the acceleration also given AG2 is I think the text wrong. Huh? It's not 270. Yeah. They give us 68.584. So, and also the angle is negative 89.4. Okay. So that's why when you calculate it, we do the cos first, cos negative 89.4. So you will be getting 0.718. Okay. If you take 584 sine, wait, 68.584 sine negative 89.4. So you will get negative 68.58. Right? So same as here, the AG3, I think the textbooks did the error there. So we have 87.715. So angle given 254.4. So probably we will get 86.715 cos 254.4. So we get negative 23.59. And then you also have the other one, it will be minus 84.48, right? So this is a value. So this is from the questions. So this one, you calculated the xy, right, based on the angle given. Then same thing for FP, we have 222, 222.41 Newton at the angle of negative 45. So this one straight away we can use the angle in the questions because the measurement again is from the reference point. Yeah. The problem we are facing here is because the reference that indicate in the question is not at the reference point that we want to calculate the x and y. Yeah? So that's why we have to do a lot of things there. So for FP, then we can calculate the FPF, FPY. So after you get all this, then you can substitute all the value, right, into there's 4 values into all this column here, right, including the AG. So you can see it's AG. The question, just this section is wrong in the text, but when you substitute here is correct. So this AG2X, AG2Y. Sorry, right? And then this should be the alpha 2, okay? Then AG3X, AG3Y, and this is FPX, FPY, this is alpha 3, maybe I write down. Then this is RPX, FPY, RPY, FPX, right? So then this is IG3. Okay, so this 2 is the M3. This is M2. This is IG2. Okay, so this is alpha 2. So you just follow the questions. Okay, so you even calculated the value. Okay, just from there. So once we have this matrix and this one, then we can calculate this. Okay. But the good news for you is normally the questions we only ask you to do until this step. Okay? You don't have to solve this 6 by 6. Okay? Unless you have a calculator that can do matrix solution, because our normal calculators, the maximum you can do is 3 by 3 matrix. You cannot do 6 by 6. Okay? So normally the questions will only ask until this step, right? We will not ask you to solve exactly what is F12X, F12Y, and so on, right? Because this one you can either solve with your advanced calculators or using MATLAB or any matrix solution software. So for example, here it asks you if you have the calculators, right, with the matrix capability, then you can calculate all these 6 variables. So you just key in and then you can solve it. You can also solve it manually. You just solve the 6 equations simultaneously. Yeah, but I don't require you to do it for this class. Okay. So normally we want you have to show me at least you understand the concept, right? So you can develop this matrix correctly, right? Because after you get this matrix, basically the rest of it is just a mathematic solution, right? So this is the critical one. So you have to understand each of these properly, how it actually look like in the diagram. That's why then only you can find the correct angle to do your calculation. Okay. So this is the thing. So we have x12x, f12y. So then based on that too, then we can calculate the force is 180 at an angle of negative 162 0.96 degrees. Then we have F32. Okay, so these two values come here. We will get 173.66 Newton at the angle of -3. Then F13, right? X, right? So because we have, if you have the mu, is mu F13X, so then we can calculate the F13Y as well. So from there, F13X, F13Y, then we can calculate the F13, which is 27.19 with the angle of -168.69. Then the top we have is 19.54. 548, right? So actually, what is this F12, F32 used for, right? So actually, F12 is the pin force that you experience, right? In the problem in the linkage. So we can look at the linkage we have. Okay, so this is the linkage. Right. Right, so the F12 is the force at this point. So means that actually when you calculate the F12, right, you calculate all the 360 degree. So you find the maximum, then you know how big is your pin has to be, right? The pin here, right? For example, end up you calculate the whole system now with the 360 degree. You find the F12 is, for example, 500 Newton. So that's why then you can size this pin that actually can take 500 Newton of force. Right? Then you have the F32, which is same as F23. So you find what is the force here, then you can size the pin correctly. Same as the point here at the sliding pin here. Okay, so this is how much force is actually experienced. Then you can size it properly. Right? This is I think last weekend or last week, one of your friends asked why we never consider the mass, the mg coming caused by the gravity. So if you look at here, over here we never say there is a mg force here. Okay. The reason is because in mechanics of machine, we are looking at the dynamic force. Okay. So in your static and solid mechanics, you study about your static force, right, or forces. So in my subjects, then you will learn about this dynamic force. When you use your knowledge in the static force in the solid mechanics or static, once you find these two, then you add them together, right? That should be your final design, right? That's why if you look at the bearing itself, when you are selecting a bearing, okay, if you look at the catalog, they always have the static load and the dynamic load. Okay, that's why you cannot put static mg into your calculation. Then your dynamic load will be very high, right? So we only look at the dynamic load with taking out this component, right? Because the mg will create the dynamic load on this side, right? This is caused by the mass. The mass causes the dynamic loading to the system. So it's over here. Okay? So it's have been taken care. But the downforce because of the gravity that is under the static calculation. Okay? So that's why you will find out that we don't talk about that over here. Right? So there is a 3-bar linkage. Then we can look at the 4-bar linkage as well. So this is a 4-bar linkage, right? So we are doing the very similar things, right? So we have this 9 equation. Let me check. Yes. So this is the 9 equations we have, right? So that's why again we have to find all this, and also over here, right? We have to find one by one. So this is the questions we have. So very similar. We have all these link length, mass, uh, the center of gravity. So again, this angle is not the final one. You cannot say my R12 is at the angle of 30. Yeah. So this is wrong. Okay? Because this 30 is measured from the line of center. Right? This line center is considered the local rotating coordinate system. So if we can come back here to look at this. So if this is a link 2, so I will have theta 2 here. So your just now the 30 degree is over here, is this one. But your R12 is pointing down from the center of gravity. That's why then the angle you take has to be from this x-axis, right? This one, the x from the x-axis, right? So it's not 30 degree. Yeah, that's why we have to find what is theta 2, what is a given value here. Then only we can. So if we zoom in, this is the link length. So this is R12. So for example, if this is theta 2, this is 30. So that's why we have to find this. Right? We have to find this because when you find this, we will find this one. So get the 360 minus the question mark, then we'll get the theta 12, the angle for R12. Okay. So again, it gives us all these value. As I mentioned, if I ask you this question, so normally I will not ask you all the way from the position analysis. So it will be given. And then link 3 also will be given all the value here. Right? So again, this one is not the actual angle that we will be using. So you still have to calculate because this 45 is based on the line of center, which is the local rotating coordinate system. Similar to the link 4. So you get CG is 0 degree from the line center, then this one is easy. This one we can just follow the theta 4, right? So it's also given the value. So now we move to see how we can do it. All right, so just now it gave us 76.2. So the angle we get is it gives us 30 degree from the line center. Okay. So that's why then we have to see what is our theta 2. Okay. So maybe we move. Okay, so again, theta 2 gives us 60. And then another, are we in the right? Oh, yeah. Then another 30 degrees. From this is line of center, all right, for link 2. So the central of gravity will be here, right? So it gives us 76.2. So remember the one we measure is from the center of gravity. That's why the angle we are going to take is from here. So 60 plus 30 is 90. That's why this is also 90. So here is 270. Okay? So that's why this one leads us to uh, to the angle here 270. Okay, so when we calculated R12 is 0, R12 X is 0, R12 Y is negative 0.0762. Okay, so there's a negative because it's pointing down. Then R32, so I only show you some of the link only. So again, this is 60, this is 127, and then I have 30 here, which is 76.2 here. That's why now I want to find my R12. Okay, so again, we use the cosine rules. 0.0762 square, 0.127 square minus 2, 0.0762, 0.127, then cos 30 degrees. So from here, you will find, just give me some time, so I have calculated. Square minus 2 times 0.0762, 127 cos 30. So maybe I write now this value first, 5.1737 times 10 power of minus 3. So we just square root it. So we get 0.0719. Okay. Then we can find the angle here. Okay. So we have 0.0719 divided by sine 30 equal to 0.127 sine beta. So we can find the beta. Okay. So same thing. So this is how we find the 28. Actually, it's same as the question just now. So we get the 0.0635 and also 0.0338. Then R23, okay, so it's still the same. Do you guys want me to show you how to find it? If not, I will just go through. Anyone? Okay, maybe you try. You try out how to find this. Don't see that I post this seems to be so easy. I just value this and then find the cos R12 cos R12 sine. The hidden difficulty is over here. It's not this one. Alright. So you must define this correctly. Then only you can find this easily. Okay, so same thing happen. I find this and also the link 4. Okay, so as I mentioned, link 4, it mentioned that the center of gravity is uh, let me see, is where is my link 4? It is a 254 millimeter long with a 127 millimeter at the 0 degree. That's why we follow the theta 4 because it's 0 degree. Okay, so that's why we follow the theta 4 here. Okay, so R14 you have to find the opposite one. Okay, and then RP is given, so we can find XY. Okay, So again, the accelerations is given. Okay, so this one is the correct one. So 47.7 at the angle. So again, we can find x and y for AG2, AG3, AG4, and FP3. So this is the correct one. Just use the angle given in the questions. So then we can find FP3x, FP3y. So again, same thing, we will plug into the matrix. So this is the answer normally if I ask in the midterm or in the finals. So we only solve up to this stage, okay? Because now this one has 9 unknown. And I don't expect you to solve the 9 unknown in the exam. So you have to build. That's why sometimes you could just ask you to construct the dynamic force analysis matrix, build the matrix. Okay. So this one you can look back at the because now your midterm and the final assessment is all open book, so shouldn't be that difficult, right? Because once you can build this, there is no question at all for you to fill up, right? This matrix, right? Because you can refer to the matrix that you have. So if you have those calculator with the matrix capability or using MATLAB and so on, so you can find each of these value. So again, you can find each of the pin force on the 4-bar linkage. So do remember when we do this calculation, is only at the specific location. For example, this one is only at the theta 2 is 60 degree. Right? When theta 2 becomes 61 degree, all these 4 value will have a new value. Right? It will be you will have a new value. Okay, so these are the two questions you have to do. So mainly is to build the dynamics force analysis matrix. Okay. So now we will continue to look at, just now I mentioned there is a pin force, right? And then we also calculated the T12, right? So T12 is the top pin, the pin force is the F. But when you talk about shaking force, normally we refer to the force acting to the ground link, which is the link 1. And also shaking torque, normally we refer to the T12, right? So as I mentioned, just now the question theta 2 is 60 degrees, so we get a set of F12 and also the T12. But then if I change to 61 degree, so your F12 will have a new value, T12 will have another value. Okay? That's why this F12 and T12 is keep changing at every angle. Okay? That's why it will become a shaking force and the shaking torque to the system. So that's why the net effect of the dynamic forces fell on the ground plane or the link 1, as this can set up vibrations in the structures that support the machine. So previous the 3-bar and the 4-bar linkages, only 2 points at which the dynamic force can be delivered to link 1. So which is the, or we call it the ground plane, which is the O2 and the O4. O2 and O4. So more complicated mechanism will have more joints with the ground plane. So the forces delivered by the moving link to the ground at the fixed O2 and O4 are designated as F21 and F41. So in our, that's why even the textbook say in our subscript convention. So you take another author book, they will use slightly different. Right? So this is just an explanation why we calculated all these F12 and T12. So again, F12 is just is equal to negative F21, and also the F41. Okay. Okay, so as I mentioned before, the uh, Newton's second law of motion, we can actually find all these internal force, this F12, F32, F41, and so on. So, but in some cases, actually, you have or you don't require to find the force in the link. So, what you are interested is the torque only in the system. Okay, so one of the method we can use is virtual work. Okay, so velocity data is needed if we are using virtual work. So in the Newtonian method, so what we use? We use acceleration. Right? In the virtual work, we use the velocity data. Right? That's why here it says velocity data will not needed in the Newtonian solution. But for virtual work, we have to use the velocity function. So this is the equation we have, right? So that's why the K is the link. So the link number 2 to the final link we have. So if we have a 4-bar linkage, so it will be link number 2 to link number 4. So N it will be 4. Okay. So there is a force times the velocity, and then torque times the uh, omega, right? So the other side will be mass multiplied with the acceleration's velocity, and then this is mass moment of inertia multiplied with the alpha, and then multiply with the omega, right? So that's why this is F, MA, this is torque, I alpha. So what we can do is we can expand the equation above, right? So what are the external force that we experience, right? So in the linkage, normally we can have either the force at the link 3, then we have to find the velocity at that point as well, and then the external force at the link 4 and the velocity at that point, right? Then the external torque T12, the angular rotation velocity again. This is angular velocity. Whether there is a T3 or not, and then multiply with the angular velocity of the link 3. And then we have external torque on link 4, multiply with the angular velocity of the link 4. So if you notice that the left-hand side equation is all the external forces and torque. Right? So the right side here, which is over here, the right side, or we can see over here, is all the inertia, the internal effect. So we have the mg is the force multiplied with the vg2, and then m3ag3 multiplied with the vg3, and then m4ag4 multiplied with the vg4. So we also have ig2 alpha 2 multiplied with omega 2, Ig3 alpha 3 multiplied with the omega 3, and also the Ig4 alpha 4 multiplied with omega 4. Alright, so that's why if you look at here, there is nothing about the F12 and so on, right? So all the force is disappear. So but the problem now is this is still a vector form, so we cannot add or multiply it directly. So what we have to do is we expand it so that it becomes a scalar equation. Okay? So means that everything we break into x, y, and so on. Okay. So this is actually normally the final equations that we are going to use. So you can see it later in this example. So we are still using the 4-bar linkage because we want to compare the result. So we have 122 millimeter long crank. So it gives you the mass, the same data, the location of center of gravity and so on. But now the issue here, the difference here is now he gives us angular velocity, angular acceleration. But now he gives us the velocity, right? At the G2, right? So similar here, it also gives us the velocity of the center of gravity at the link 3, and also the velocity of the center of gravity for link 4. So to solve it similar way, we still have to expand it to x and y. And so again, this is given. This will be given, right? As this is acceleration data. Okay? So we will find the xy component. So we also have the external force. We only have FP3, there is no FP4. And then the velocity, we break it into x and y component. Okay. So what we do here is now we have all this value, okay, over here and here. So we will substitute into the equation. That's why just now I say that this is the equation that you use. Right? You just substitute one by one. So we don't have FP4. So this will be 0. T3 no, T4 no. Okay. So that's why all this will be disappear. So that's why if we substitute, we get the whole thing, and then actually if you notice that only T12 is the unknown in the whole equation. So from here, then you should be able to find your T12, which is 33 Newton meter. So the K is not kilo, K is just representing the z-axis. Right? So it's 33 Newton meter. So you can see that by using this virtual work method, we can find T12 straight away. Right? But the problem is we will not be able to find all the internal force on the linkage. Right? Okay, just now we talked about the shaking torque. So that's why we can actually control the variation of the torque. So we use these flywheels. Okay? So a typical large variation in acceleration within the mechanism can cause significant oscillation in the torque as well. That required to drive it at a constant or near constant speed. So the peak torques we needed may be so high to require overly large motors. Okay. So what happened is that when you calculated a system, okay, so we calculated every degree of rotation, then we found that what is the maximum torque. So in order to make sure that the motor we are going to install onto the linkage can drive the linkage at the desired specification of the movement. So we have to size the motor which has a torque which meet the maximum torque of the linkage. Okay. So but sometimes this maximum torque is only happen in a very short while, and the rest of it the torque is very low. So if you sizing that the motor according to the maximum torque of the linkage, then your motor has to be oversized, have to be very large. And when you grow the size of the motor, actually you also grow the cost of constructing your whole system. That's why sometimes we can. That's why most of the time we want to size the smallest possible motors into the system. So how to reduce the peak torque? So one of the way is to use these flywheels. So that's why to size the flywheel. So normally we will look at the average torque over the cycle, right? So this could be due to mainly to the losses and the external work done may often be much smaller than the peak torque. Huh? So how to smooth out the oscillation in the torque during the cycle? So the convenient and relatively inexpensive way is to use the flywheel. So now we look at the torque variation. So figure 18-8. So it shows the torque that we have over here. Right? So we found that this is 0. So sometimes the torque can go to the negative side. So means that instead of you have to supply torque, the linkage will actually give you the torque value. So figure 18-8 shows the variation of the input torque from a crank rocker 4-bar linkage over one full revolution. Right? That's why just now if we calculate the 60-degree, we are only calculated this point only. So that's why in order to plot this graph, the nine equations that we're trying to solve, we have to solve for every angle, right, in order to get all these points, right? So you have to do a lot of time in order to calculate this. If, for example, our resolution to plot this graph is 1 degree, so you have to do 360 times, right? In order to, you have to solve the 9 equation 360 times in order to plot this graph, right? So in this case, the system run at the constant angular velocity of 50 radian per second. The torque vary a great deal within one cycle of mechanism, going from positive peak of 38.9 Newton meter to the negative of 18.9 Newton meter. So the average value of torque over the cycle is only 8 Newton meters. So you can compare. So the peak 38.9 Newton meter, the lowest is minus 18.9 Newton meter. But if you find the average torque in this whole cycle is only 8 Newton meter. Right? So the question now is, are you going to size the motor with the 38.9 Newton meter, or can we just size the motor according to the 8 Newton meters? This linkage has only 54 Newton external force applied to the link 3, right? And also 2.8 Newton meter external torque applied to the link 4. So this small external load cannot account for a large variation in the input torque required to maintain the crank speed. So why this happened? Right? The large variation in the torque are evident of the kinetic energy that is stored in the linkage itself when they start to move. So we can think of positive pulses of torque as a representation of energy delivered by the driver or the motors and stored temporarily in the moving link. The negative pulses of the torque is an energy attempting to return from the linkage to the driver. Okay, so this is what we have. And below here, it also show you the DC permanent magnet electric motor's typical speed torque characteristic. So that's why when you choose a motor, you have to find this graph from the supplier, because when they say this motor rated torque is, for example, it says rated torque is, what is the rated torque? So for example, it says rated torque is 300 Newton meter, right? So it doesn't mean that your torque with a different speed, your torque will always 300 Newton meter. So you can see that at the lower speed, it has a higher torque. At the higher speed, it has a lower torque, right? So that's why when you choose motors, you have to know what is your required motor speed and what is your required torque at that speed, right? Then you have to find from the graph. Okay, you cannot purely based on the rated torque and the rated speed, right? So figure 11-9, the one, the speed torque characteristic of the permanent magnet DC electric motors is shown there. So other types of motor will have a differently shaped function that relate motor speed to the torque. We can also find it as a figure 2-41. But all drivers will have such a characteristic curve. So as the torque demand on the motor change, the motor speed must also change accordingly. Yeah. So because this is its own characteristic. So this means that the torque curve being a demand in figure 18-8 will be very difficult, right, for a standard motor to deliver without drastic change in the speed. Okay. So what it means here is when your linkage torque requirement is increased, so your motor may spin slower. When there is no more, the torque requirement from the linkage is reduced, your motor will spin faster, right? So then it will cause a problem. Instead of now I want my linkage, the link 2 is rotate at a constant speed of 50 radian per second. Once you plug in this model, you will find out when you start to run it, you will find out, your link 2 now it doesn't rotate at the constant speed. It actually rotate at a very speed because of the torque, right? So the computations of the torque curve in figure 18-8 was made on the assumption on the crank. Those speed was a constant value. All the kinematic data used in the force torque calculation were generated on that basis. That means the rotating speed of the link 2 is constant. So with the torque variation shown, we would have to use a large horsepower motor to provide the power required to reach that peak torque at the design speed. So the power is equal to the torque multiplied with the angular velocity. So we have a peak torque of 38.9 Newton meter. So we can calculate the peak power because the angular velocity required is 50 radian per second. So we will find out that the peak power that we need for the system is 1.93 kilowatt. Right? So what can we do? So the power needed to supply an average torque is much smaller. Okay? Only 8 Newton meter. You multiply. Okay? 8 Newton meter. Where is the meter? It has to be Newton meter. Multiply with 50 radian per second. So means if we base on the average torque, the average power is only 0.397 compared to 1.93 kilowatt. Okay? You compare it. So there is a lot higher. Okay? So it would be extremely inefficient to specify a motor based on this peak power, right, of the system. Okay? You can go and check that the motor with 0.4 kilowatt or 0.5 kilowatt compared to 2 kilowatt. So the price is not just times 4. Okay? And also if you size the 1.93 kilowatt motor, the energy consumption from the motor is also higher. So one of the way to solve it is to use what we call it a storing kinetic energy device, or which we call it the flywheels. Okay. So flywheels designed as a flat circular disc, so it will attach to the motor shaft. So this is the motor shaft, this is the motor, and then you just attach. So Now we try to see how the flywheel can be used. So the motor supply a torque magnitude of Tm, which we would like to be used as a constant as possible, and to be equal to the average torque, T average. So on the other side of the flywheel, demand the torque is L, TL, the demand torque from the linkage. That's why it's TL, which is time varying as shown in figure 11-8. So what happened now is our motor will not directly attach to the linkage, but actually in between we will slot in the flywheel. So kinetic energy can be calculated as half I omega square. Okay. So now we look at that. We use again, this is Newton's second law, summation of torque equal to I alpha. So we have the torque from the motor, torque from the linkage, right? So TL minus Tm, then it should be equal to the I alpha, which is the inertia from the system. But the thing now is we try to make our torque of the motor as close as the average torque, so we can replace the Tm to T average, right? Then alpha, it can be written as omega d omega over d theta, so we can just replace it here, right, in the equation. So then we try to rearrange, so we can say that the TL minus T average d theta, and then I omega d omega. So then we do the integration, right, from the minimum omega to the maximum omega here, right? So this is a derivation. So we will actually get this function. So left side of the equation, change in the energy between the maximum and minimum shaft omega angular velocity, and it is equal to the area under the time diagram, right? So because when we do the integration, actually we are trying to find area under the curve. So it should be here, here, and here. Okay. So means the top two will minus the bottom two. Right? Then we will find the average torque actually. Okay. So right side of the equations is the change in the energy stored in the flywheels. So the only way to extract energy is to slow flywheels down. Right? Adding energy will speed up the flywheel. Okay? So those is impossible to obtain exactly constant shaft velocity in the phase of changing energy demand by the load. The best is to minimize this. Okay? So we are trying to minimize this only. Okay? So on the other way of saying is that it's impossible for you to make the function shows the input torque curve is average value. So that is IMF.
Sir, you're lagging.
So in this, you can't hear me. Can you hear me? Oh,
Cannot.
now only my slide change. Yeah. Now is it okay? Is now okay? Hello. Is now so still lag a bit. I quite slow because I already turned off my screen sharing. Okay, have you guys so fast go to the toilet already? So you can come back, huh? So now you can hear me? Okay, I have to turn off my mobile to the airplane mode and back on. I think I've been using too much data. The DG stopped me. Okay, so we can still continue on the fly view. Okay, so here it gives us the torque curve for the torque required from the linkage, the variation. Then we have this average value and the RMS value, right? So if you look carefully that actually this is what we do, we the calculation. So we have a positive value here, then the negative value here, right? So that's why we can do the summation, right? In order to find this average line, right? Where is the average? So what we do is calculate the average value of the torque time function over one cycle. So then we find out that it is actually 8 Newton meters. Note that the integration on the left side of the equation 2.8c is done with respect to the average line of the torque function, not the respective theta axis from the definition of the average. And then the sum of positive area above an average line is equal to the sum of the negative area below the line. Right? So what it means here, if now I cross this, that's why the whatever we have here plus this one is equal to this one plus this one. Okay. So the minimum omega will occur after the maximum positive energy has been delivered from the motor to the load at point theta. So where the summation of positive energy in the top pulses is at its largest positive value. So the maximum omega will occur after the maximum negative energy has been returned to the load, right? So this is mentioning the rotation flywheels. So at the point where the summation of energy in the top pulse is at its largest negative value. So to find this location in theta corresponding to the maximum and the minimum omega, and those find the amount of energy needed to be stored in the flywheels. So we need to numerically integrate each pulses of these functions from crossover to crossover with the average line. So here we label A, B, C, D. So if you can see that, so we have to calculate it one by one. A, B, C, D. So because this is one cycle, so it will return back to A again. So we have to find this one by one. So as shown in figure 11-11, the positive and negative pulses are separately integrated as described above. So reference to the plot of the torque function will indicate whether a positive or negative pulse is the first encounter in the particular case. Accumulate this pulse area. Table 11-1 shown this purpose. So we'll look at the table here. Okay. Note in table 11-1 that the minimum shaft speeds occur after the largest accumulated positive energy pulse, 28.84 Newton, has been delivered from the drive shaft to the system. So this delivery of energy slow the motor down. The maximum shaft speed occur after the largest accumulated negative energy pulse, which is negative 6.87 Newton meter, has been received back from the system by the drive shaft, right? So this return of energy, stored energy, will speed up the motor, and the total energy variation is the algebraic difference between these two extreme values, which is negative 29.7 joules. So this negative energy come out from the system need to be absorbed by the flywheels and then return to the system each cycle to smooth the variation of the shaft speed. Okay, so what happened here is you can see from point A to point B, we have this positive 22.84 joules of energy that have to supply to the system. Okay, so that's why when we sum it up, because this is a starting point, so you just do the summation of the energy, so you will get a positive 22.84. Okay, then second graph there. So if you go back to this one, okay. So second one we have negative 29.71. Right, so what we do is we put it here. From B to C, we will gain this 29.71. So what you do is then this one plus this one. Okay, 22.84 plus negative 29.71. That's why we get negative 6.87. Okay, then further look at the graph we have. Okay, so we have another one positive 17.51. We plug in here. So again, this one plus this one. So we get positive 10.64. So again, this one plus this one plus. So we plus negative 10.4, then we will get this 0.17. Okay. So what happened here is from here, then you will indicate the highest positive value, the largest negative value. So the highest one will indicate the minimum omega. The biggest negative value, it will be maximum omega. So we can find out where it is, right? And then from here, then we can calculate the total energy required here. So it's negative 6.87 minus 22.8. So we get negative 29.71 joule. So this is the total. So we total it up. Okay. So now we can size the flywheel. Let me see. Yeah. Right, we will use the value just now to size the flywheel. So to determine how large a flywheel is needed to absorb this energy with an acceptable change in the speed. So the change in shaft speed during a cycle is called the fluctuation. Okay. As mentioned just now, there is no way you can make a constant rotating speed when you have unbalanced linkage. So what we are trying to do is to minimize the speed variation. So one of the things that we define is the fluctuation, FL. So the FL will define what is the difference between the maximum omega and the minimum omega. So the smaller the FL or the fluctuation you set, then these two, the value has to be close enough, right? So normalize this to a dimensional ratio by dividing it by the average shaft speed. So this ratio will be called coefficient of fluctuation, right? So it means that we divide both sides with the omega average, right? That's why then here we will get the coefficient of fluctuation. So here we will get the formula stated here. So normally the coefficient of fluctuation typically is between 0.01 to 0.05, right? Which means the fluctuation is about 1 to 5%, right? The shaft speed. That's why if you ever measure rotating speed of a system, right, with a motor, so you put we can use a tachometer. So you put your tachometer onto the shaft, then you will find out that your shaft speed is jumping up and down, right? So that is where you have this, right? The fluctuation, right, of your rotating speed, right? So the smaller this chosen value, the larger the flywheel will have to be. Yeah, right? So the large problem of large flywheel is it will add more cost. Okay? I think normally this is not the biggest issue because flywheel generally it's just a piece of metal, a heavy piece of metal. Most of the time the problem comes from here is the weight. Right? When you increase a large flywheels, you also have to increase the weight, right? And also the size, right, of the flywheel. That will create the problem, right? So the required change in the energy by integrating the torque curve, right? So just now these formulas we already seen before, right? And also the right side also we've seen before this one, right? So what we do is we can factoring this equation, so it become omega max square minus omega min square because of these two. So we can write it in this form. So if the torque time functions were pure harmonics, then this then is the average value. So we can find the average value, right? Omega max plus omega min divided by 2. So what we do is then we do the substitution, right? Over here, there's the right. So what you can see is a second. What you can see here is see omega max minus omega mean will be k omega average, right? Remember, so that's why we get this. This will be k omega average. Omega plus omega max plus omega mean, we will get 2 omega average, right? 2 omega average. So that's why here we get this equation, right? Then we try to rearrange it in order to find the I, because if you look at the whole equation, this is the average rotating speed. This is the coefficient of fluctuation. So then this is the only one related to the flywheel. So we can rearrange this equation and then make it to the function of mass moment of inertia for the flywheels. So the equation above can be used to design a physical flywheel by choosing the desired coefficient of fluctuation k. So using the value of E from the numerical integration from the torque curve, right? Then we can compute the mass moment of inertia for the flywheel, right? Or we call it the system. The most efficient flywheel design in terms of maximizing the mass moment of inertia for minimum material use. So my mass is concentrated at its rim and is hub supported by on the spoke, right? So that's why a lot of time you will see the flywheels, you only have material outside. So then you cut some holes here to reduce its overall weight, right? So this is a hole, you cut the hole, right? So your weight is all concentrated on the outer edge here, right? So this is how they design the flywheel. Huh? So in our case here, we choose the coefficient of fluctuation is 0.05 or 5% here. So what you mean here is the k, which the k is we choose 0.05, and then the e that we have just now, okay, 29.71. So then we will find out that this will be our torque curve, the new torque curve now, right? So you can see that there is relatively smaller, the variation becomes smaller. So means hence you now, if you look at it, right, your required torque from the motor peak at this maybe around 9.9 Newton meters. Okay, so this is how we average it. Instead of our initial torque look like this, right? So after adding the flywheels with this uh, fluctuation of 5% on the velocity, so we'll reduce from maybe just now is 30. What is the value? 38.9, yeah, right? The peak torque from 38.9 all the way down to maybe about 9.9 Newton meters. So you can see the huge difference, right? But always there is a problem on the inserting the flywheels. As I mentioned, is the width and the size, right? So the flywheels will increase the size of your system, right? Okay, I think that's all for the topic on the dynamic force analysis. So on Wednesday, then we will move to balancing. So in another word, also the coverage for your midterm is done on today. So Wednesday we will move to the topic on balancing, which is not in your midterm test, right? So balancing, I think you may actually touch on it a little bit before. So we'll still go through, especially on the dynamic balancing, not the static balancing, right? So these are the topics that we'll cover in the balancing, right? So we'll look at the static balancing again, dynamics balancing, and then measuring and correcting the imbalance, right? Then the other one is balancing the linkages, right? So what is the effect of balancing on the shaking and pin force, and also the input torque? And then balancing the shaking moment in the linkage as well, right? So these are the things that we'll cover in the balancing. Uh, I think that's all. We can end our class now. Okay. So any questions? Or most of you still like to ask me questions after the class? Okay. So I think Wednesday I have to choose to do the lecture in my house. Okay. My 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 fiber connection, internet connection is more stable than over here. Okay. So if no questions, thank you very much for attending the class. So you can quit. Or someone suggests me to go to computer lab. Computer lab, I'm not sure there is a people or not. If there is other people, then I cannot conduct class. So I'm now in my office at the 8th floor. Right? From 20 years of from today lah. From today onward, any one of you who has a need to come back to the campus, you can apply to the FGO. You can send the email to FGO and explain, send a reason, a simple reason on why you want to come back. So then they should be able to issue you a letter so you can come back to the campus. For example, if you really want to meet your academic advisor face to face and so on, so you can apply it, right? To meet your academic advisor, or even you want to see me, so you can come. Okay? But you need to send the application. You need to apply first. You cannot walk. There is no walk-in. So if you come straight away to the campus, the security guard will stop you at the main entrance. You must be able to show the approval from the faculty before you can enter the campus. Okay. So far, I think the notice from the new master is already out. This trimester, we will still go for online teaching and learning, basically. But October, most likely, we will back to normal face-to-face class, right? But there is still some discussion, the final discussion on, because some of you may depending on the situation, some of you may be still very concerned about the safety. Yeah, so university is also looking at that, whether there is a possibility of some of you can do online classes also, right? So I think thank you very much. So I will see you on Wednesday again. Okay, bye.